This is your presenter Asloob Mudassar, and I am presenting slide number 46 of the course on laser physics. Question is, describe homogeneous and inhomogeneous line broadenings. How the transition probability in a two-level system is affected due to collision broadening. The answer is, a line broadening mechanism is referred to as homogeneous when it broadens the line of each atom in the same way. The line shape of a single atom and that of the overall absorption cross-section are identical. A line broadening mechanism is said to be inhomogeneous when it distributes the atomic resonance frequencies over some spectral range. It broadens the line of the overall system without broadening the lines of the individual atoms. Homogeneous broadening occurs when an atom encounters a collision with other atoms, ions, free electrons, and with the walls of the container, and is also referred to as the collision broadening. In solids, it is due to the interaction of atoms with the lattice phonons. On collision, the wave functions of the two levels which are given over here, these two wave functions in an atom may undergo phase jumps, resulting in random phase jumps in the oscillating dipole moment, which is given as mu oscillation. Oscillating is equal to real part of 2 into A1 A2 star into mu 2 1 into e to the power iota omega naught t. This mu oscillation has been described in much detail in slides number 44 and 45. So the phase jumps resulting in random phase jumps in the oscillating dipole moment of the atom with respect to the incident electromagnetic wave. So let me read again. On collision, the wave functions of the two levels which are given over here, these wave functions in an atom may undergo phase jumps, resulting in random phase jumps in the oscillating dipole moment of the atom with respect to the incident electromagnetic wave. Collision thus interrupts the process of interaction between an atom and the incident electromagnetic wave. Relative phase is important during the interaction process. Rather speaking, in terms of the phase jumps in the oscillating dipole moment of an atom, we can equivalently say that the phase of the electric field of the incident electromagnetic wave undergoes a phase jump on a collision. In figure question 46.1, the incident electric field E of t is shown encountering phase jumps at collision points C1 and C2. So look at this figure. The caption is incident electromagnetic wave undergoing phase jumps at collision points C1 and C2. So the collision points are located at C1 and C2, separated by time tau, and the electric field during the collision, you see that there is a discontinuity in the electric field at the position of the collision, and this discontinuity in the electric field give rise to the phase jumps. Due to phase jumps in some part of the electric field in the incident beam, the electric fields combine in such a way that the incident beam is no longer monochromatic to the atoms on their way. We define d rho is equal to rho nu prime d nu prime as the energy density of the wave in the frequency interval between nu prime and nu prime plus d nu prime. The elemental transition probability represented by dW12 from level 1 to level 2 depending on d rho thus becomes dW12 is equal to 2 pi square 3 divided by 3 n square epsilon naught h square multiplied by the absolute square of mu 12 multiplied by rho nu prime d nu prime and multiplied by delta of nu prime minus nu naught. This elemental transition probability has already been discussed in one of the previous slides. So to obtain the overall probability, transition probability, we need to integrate both sides, and the result is shown. So on the left hand side we have W12, and on the right hand side we have all the terms as previously defined, except that we have the integral from minus infinity to plus infinity over the frequency element d nu prime, and the integrands are rho nu prime delta of nu prime minus nu naught. Here we can replace rho nu naught as defined below, that is rho nu naught can be replaced by rho into g of nu prime minus nu, where rho is the energy density of the wave given by rho is equal to n square epsilon naught into E naught square divided by 2. And g of nu prime minus nu describes the spectral density of rho nu prime. Thus substituting or replacing rho nu prime in the integral on the right hand side of the expression of W12 by its value, which is rho g nu prime minus nu, we obtain the results as shown. So W12 is equal to 2 pi square divided by 2 n square epsilon naught h square multiplied by the absolute square of mu12 into the integral of rho g of nu prime minus nu multiplied by delta of nu prime minus nu naught, and the integration limits are from minus infinity to plus infinity, that is the sum over all emitted wave frequencies, and the frequency element is d nu prime. So this W12 can be written as, after performing the integration, we have the result shown in equation number 46.1. You see that in obtaining this result we have used the property that delta within the that is the argument of the delta function should be 0. For that one, nu prime should be equal to nu naught. So setting nu prime is equal to nu naught in the function g, we obtain the result. But you see that we have changed the order, that is we have rather writing nu naught minus nu, we have replaced the argument by nu minus nu naught, because the function g is an even function, or we can say that it is symmetric about the horizontal axis. So we have written W12 as given in equation number 46.1, where we have used the fact that g of nu minus nu naught is symmetric about nu naught. The normalization condition of g of nu prime minus nu can be established by integrating both sides of rho nu prime is equal to rho into g of nu prime minus nu. So integrating both sides of this shown in red, we have these results. On the left hand side we have the integration from minus infinity to plus infinity, and the integrand is rho of nu prime, and the integration is with respect to d nu prime. And on the right hand side we have plugged in the value over here, that which is rho g of nu prime minus nu, and the integration limits are the same. And then we have taken rho common on the right hand side expression. We have taken rho common, and the rest of the integral is from minus infinity to plus infinity g of nu prime minus nu, and the integration is with respect to d nu prime. So if you look at these three integrals, look at the leftmost integral. So you see that leftmost integral will give you the value of rho, that is the total energy density. So we can replace it with rho on the left hand side, and we have used the rightmost side of the expression which is given. So you see that the rho will cancel out from here, and then we are left with integration from minus infinity to plus infinity g of nu prime minus nu, and integrated with respect to d nu prime is equal to 1. So this gives you the normalization condition of the function g. So here the function g of nu prime minus nu represents the normalized spectral density of the incident radiation. So you see that we have addressed all the aspects of the questions, that is the aspects concerning with the homogeneous and inhomogeneous broadenings, and we have also derived the transition probability for a two-level system under the collision broadening. So all these setups have been discussed, and if you come across any things which are new to this slide, that is functions psi1 and psi2 and the oscillating dipole mu OSC. So if you find them new, then you should consult the previous slides so that you can get familiarity about these things, and then you can very easily understand about all these mathematical discussions that we have carried out in this slide. So with this one, this is the end of slide number 46.